We've looked at electrons. Now let's look at protons and neutrons and how they come together in the nucleus. Our modern view of the atom and the nucleus comes from the work of Ernest Rutherford and his famous gold foil experiment. Alright, so what is this famous gold foil experiment we keep hearing about? In order to understand Rutherford's work, we first have to understand how atoms were viewed at the time Rutherford was working. At the time Rutherford was working, people believed in the plum pudding model. Now, we don't have plum pudding in the States, so that model doesn't really do us any good. We're much better off thinking of it as and I'm sure I'm misspelling tapioca, the tapioca pudding model of the atom. Scientists believe that atoms were like tapioca pudding. You had a big pudding, and that big pudding had a positive charge. And inside that positively charged pudding, you had these little negative electrons scattered about, just like tapiocas in pudding. But the point was that the tapioca pudding viewed the atoms as solid mass. I didn't say this model was correct. I simply said this was the model of how atoms were viewed. Rutherford designed an experiment to test the tapioca pudding model of the atom. What he did was he took a thin piece of gold foil and he placed it in the center of a zinc sulfide screen, and then he took a radiation source. And this just wasn't any radiation source, it was a radiation source that shot alpha particles. Alpha particles consisted of 2 protons and 2 neutrons. What does that mean? Well, we know that protons and neutrons have mass. So he was shooting alpha particles that had mass, a mass of roughly 4 AMU. And not only did they have mass, but if they had 2 protons, that means they had a charge. And not just any charge, but a positive charge. So he shot these alpha particles that had a positive charge and mass, and he shot them at some gold foil. Now, this zinc sulfide screen was placed around the gold foil. If an alpha particle strikes a gold foil screen, it makes a nice little, they use red here, it's actually sort of a greenish glow whenever the alpha particle hits that zinc sulfide screen. So he was able to tell where the alpha particles were going when he shot them at his gold foil. Now, if the plum pudding model of the atom was correct, what should happen when the alpha particles hit this screen? Can matter go through matter? No, 2 things can't occupy the same space at the same time. Not a theoretical physicist or chemists. So he shot these alpha particles at the gold foil, and if the plum pudding model was correct, matter can't go through matter, so it should have been like slamming a tennis ball into the side of your house. It should bounce straight back at you. If the plum pudding model was correct, then all the alpha particles he shot at the gold foil should be returned directly towards the source. So, knowing that the plum pudding model was right, Rutherford sent his graduate student to the basement of the chemistry building to perform the experiment. Well, what happened when the graduate student shot the alpha particles at the gold foil was that the majority of these alpha particles went straight through the gold foil like it wasn't even there. If the majority of the alpha particles went straight through, what does that have to mean about the gold foil? Matter can't be in two spaces at once. So if the alpha particles that have mass, the majority of them went straight through the gold foil, that has to mean that the gold foil is mostly empty space. And that if atoms are what makes up the gold foil, then atoms themselves have to be mostly empty space. Since the majority went straight through, atoms have to be mostly empty space. The graduate student also observed a couple other things. The graduate student observed that while the majority of the alpha particles were going straight through the gold foil, some passed through but were deflected at an angle, and others didn't pass through at all. Instead, they were bounced back. Now, the graduate student went and told Rutherford about these results, and Rutherford said, "My word, you're an incompetent moron. I give you a simple task to prove an existing model, and you blow it. Get out of my sight, you incompetent ninny." So, Rutherford goes to the basement of the science building himself, because if you want something done right, you got to do it yourself, and he repeats the experiment, and guess what? He gets the same results as the grad student. So what does he say? He says, "Eureka! I'm brilliant!" And he concludes three things. First, as we've already discussed, he concludes that atoms must be mostly empty space because the majority of the alpha particles went straight through. Second, he explains the alpha particles that didn't pass through but were deflected. He said that if the alpha particles were deflected, they were deflected because they were hitting something. Right? If matter hits matter, it bounces back. Therefore, there had to be small, dense centers of matter. In other words, there had to be some sort of matter inside an atom. They couldn't be entirely empty space. So there had to be a small, dense center of matter in the atom. Okay. If I'd been running the experiment, I could have made this conclusion, and I could have made that conclusion. Where I think Rutherford made a true leap that I might not have gotten right off the top of my head is in how he explained this third group of data here. How he explained the alpha particles that passed through is how he explained the particles that passed through but were deflected at an angle. And I've gotten really messy here. Let me clean things up real quickly. How he explained this row right here shows true brilliance. He said that if these things were being deflected, it was because of charge. Remember, we said that these alpha particles had a charge of positive 2. What happens when you bring two north ends of a magnet together? They push each other away, right? So he said that if my alpha particles have a positive charge and they're traveling through empty space and something's pushing them to one side or the other, whatever is pushing them to one side or the other has to have a positive charge. Therefore, he said that the small dense center of matter that he was talking about earlier had to have a positive charge. And if it had a positive charge, that meant that the protons had to be located there. Not only that, but all matter in the atom had to be located there, so the neutrons had to be there too. So let's summarize. Before we summarize, however, why don't you write down Josh? Write down Josh. Josh. Josh Levinson. You don't have to write down Levi's son, but write down Josh. Write down Josh, Josh. Just started the 4th season, and I'm really enjoying how they've now made Josh like a reverse werewolf. But at any rate, I digress. So Rutherford was able to conclude that atoms are mostly empty space, and that inside that mostly empty space, there were small dense centers of matter. And because these small dense centers of matter deflected positively charged items, these small dense centers had to have a positive charge, meaning that not only were the protons located there, but the electrons couldn't be. Rutherford decided to call these small dense centers of atoms the nucleus of the atom. And inside those nucleuses are located the neutrons and the protons. So where are the electrons if they're not in the nucleus? The electrons must be in the empty space. Alright, chemistry is easy, life is hard. Let's move on. In what sounds like the beginning of a bad joke, if atoms are mostly empty space, how empty are they? Well, if a baseball field is an atom, your nucleus would be the size of a pea. So atoms are the vast, vast majority of empty space for those electrons to run around. Your protons and neutrons are huddled in a very small space. Kind of like the survivors huddle in the prison in Walking Dead, right? Well, the zombies are able to roam around everywhere in the world. Right. This just summarizes what we've talked about, and I think it's more important for me to put it in the handout than it is for me to handle up here. You will, however, need to know the things that you see in front of you when you're working some of the problems in later chapters. So don't lose this. Matter of fact, you might want to print this out on a separate sheet of paper and save it. Because remember, we said that we consider the mass of an electron negligible, but look, it does have mass. Just 10,000 less than that of a proton or a neutron. Notice the charge of an electron is given here and the charge of a proton are given here. You will use the charge of an electron in particular in later calculations. That's it. Just save the slide. Kind of like save the date. Beep.